Greetings to everyone. My name is Chinmay Vinay Dandavate. Currently, I am in the fourth semester of the MSc Statistics program and I am pursuing this degree from the Institute of Science Nagpur, which is an autonomous college under the government of Maharashtra. The topic which I have selected to design a presentation for this course based on the multivariate analysis is the distribution of the maximum likelihood estimator, that is the MLE, of the multivariate normal distribution, which is also abbreviated as the MVN distribution. Now, given the fact that we are in the fourth and the final semester of this 2 years PG program, and that the culmination of this program is no more distant, I thought of presenting this topic from the perspective of the world which we would be facing a few months later, that is, the perspective of the real world. Up till now, the way in which we approached every topic was more or less an academic perspective, but now I would like to bring about a change and I would like to present this topic from a real world perspective. And in order to go ahead on the same lines, I would like to introduce you to a statistical equipment named as the Galton's board. So here we have this device called as the Galton's board, and I have included here a clip to demonstrate as to how this device works. So here, as it can be seen, this device is a pretty simple and pretty mechanical device with no such complex mechanism associated with it. Also, the activity which has been demonstrated by this device also is pretty obvious and in fact might appear to be quite mundane, at least to the eyes of a layman. But to the eyes of a statistician, this activity is certainly not an ordinary activity, and especially the shape which these beads have obtained after sliding down through this narrow channel and further colliding with these obstacles is certainly not an ordinary shape, because this shape is known as bell shape and it is the shape of the graph of normal distribution, and thus this is like a statistical event which has took place in front of our eyes, and this device is like an object lesson or is like a miniature form of a very wide enterprise and a very vast web of concepts which lie behind the wheel. And the agenda of this presentation is going to be an attempt to tear apart that wheel, to pierce that wheel by using our knowledge of mathematics, and to garb that concept by the language of mathematics to the maximum possible extent. Before going into the subtleties which we have discussed in the previous slide, I would like to stress a bit more on this device Galton board, since as I have said in the previous slide, it is like a miniature form of a very vast concept which lies behind the wheel, and it is like a gateway to the enterprise of multivariate normal distribution, or for that matter normal distribution in general. I would like to stress a bit more on this Galton board and what each component of this Galton board represent. So firstly we have these balls or beads. They are representatives of multiple trials. They are representatives of multiple identical trials, since all the beads are like identical. And in real life they might even represent individual members of a population which aggregate to form a pattern in case it is a case study which is going on. These obstacles, which are also known as pegs, they represent the transformation which occurs from independent beads collected randomly to a bell-shaped curve where each bead, it slides down through the narrow channel, it collides with this obstacle, and after the collision, at least on this Galton board, it has two options either to bounce to the right or to the left. And this bouncing to the right or the left direction is the actual transformation. And when this transformation, this bouncing to right and left direction occurs collectively, the beads, they obtain this bell shaped curve. And also additionally, as this red arrow indicates, the movement of the beads is from the top to the bottom direction, and the arrangement of these pegs is strictly on a single plane, which represents the transformation to be a univariate normal distribution where there are only two dimensions. First dimension, it corresponds to the dependent variable, and the other dimension corresponds to the independent variable. As I have said while showing the clip of Galton board, this journey is an attempt to tear apart the wheel and to realize the concept of normal distribution, and thus this can be very well put in this form, this pictorial form, where we can see that we have this Galton board on the left side, and from this Galton board we go towards this PDF of normal distribution. That is, the journey is to validate this shape by this equation. We have to prove that this equation is a representative of this shape, and not just to stop there, but to go a few more miles ahead and to realize as to how the same structure of concepts work in the three dimensions. But then, looking at the very mathematical representation of this normal distribution, this mathematical statement which represents the normal distribution, as apparent it is like a paraphernalia of constants. It has many constants which have came together in a particular order and have given birth to this PDF of normal distribution. As it is apparent here, there are many constants like E, which is known as the Euler's constant. There is this pi, which is approximated by 22 by 7. We have this square root 2. We have this minus half to the power of E. So what role do these constants play into this normal distribution? And as I have repeated this many a times as of now, the journey is from the incident which has took place on the Galton's board to this PDF of normal distribution. And the target here is to validate the shape which those beads have took using this particular mathematical statement. But then what can be the way to do it? What can be the immediate course of action which can be employed to exercise the same purpose? Well, the way here, or the course of action which can be employed here, is to build a street between the shape which has took place on the Galton's board to this equation. And this venture is going to be more of like a trial and error sort of venture. There are going to be many mistakes, we are going to reject a few attempts, but then we will learn something new from each mistake. And the basic course of action in its essence is going to be a replication of that particular bell shape by using our knowledge of coordinate geometry. So here we begin with this journey. So here we come to casting the first block to this pathway from the Galton board to the PDF of the normal distribution. Well, the very first question which arises immediately is why E? Why the Euler's constant? Because otherwise there are many constants in the nature and in the abstract mathematics, like the Boltzmann constant, or the Heisenberg's constant, or the Planck's constant, or the Rydberg's constant, or the speed of light, or the fundamental unit of charge. So why E? Well, the reason is the fact that the function which is mapped on this constant, which is known as the exponential function, has few very desirable mathematical properties. And the two prominent desirable properties among those many properties is the fact that this function is resistant to the mathematical operation of differentiation and integration. That is, integral of e to the power x is e to the power x itself. Differentiation of e to the power x gives e to the power x itself, and thus this function e to the power x is quite robust. And with this being the mathematical justification, we consider E as the primary unit or the primary block of this pathway from Galton's board to the PDF of normal distribution. So here we first try with e to the power minus x, and we see as to what shape the graph of e to the power minus x has. So here we can see this is the shape of the various values of e to the power minus x. We have plotted many values of e to the power minus x, and the shape which it traces is not by any way resembling the one which was obtained by the beads when they were made to fall through the pegs in the Galton board, and thus this attempt has failed. So now we consider the previous attempt as a failed attempt, and we now try e to the power x square and see as to what is the shape of this function. So here is it as it can be seen for the various values of x, e to the power x square respective values have been plotted, and the shape which has been traced by those various values this time too certainly does not resemble the shape which was obtained by those beads on the Galton board. So this attempt too has failed. So after uh, the previous two failed attempts, we now try e to the power minus x square and see as to what is the shape of the graph of e to the power minus x square. So here as it can be seen, the shape here is certainly resembling the shape which was obtained by the beads on the Galton board, and this brings about a successful milestone, and this milestone which we have obtained is necessary but is only a halfway to the street from the Galton's board to the PDF of the normal distribution, because as we have seen that the PDF of the normal distribution contains mu, it contains sigma. So we have to see as to what role these constants have to play, and these variables like mu or sigma also have to play. So now as we have said in the animation related to the Galton's board, that we have to realize the concept via using mathematics as our instrument. We have to garb the concept which lies behind the wheel in the language of mathematics, and the language of mathematics is essentially quantitative, and thus this curve, or for that matter the shape which those beads obtained, needs to be described quantitatively, and this quantification needs to be done in two aspects. First one being where does that curve lie on a given plane, and secondly what is the spread, what are the dimensions, what are the measurements of that curve. And dealing with the first aspect, location, so the location of any curve is determined by where the peak of that curve lies, and as we know in a normal distribution the peak of the curve corresponds to the mean. So here mu represents the mean, and it can be seen via this animation once again that by including mu here we can determine the location of the curve graphically. it can be seen that as the value of mu changes, so does the location of this curve, and thus this gives an ideal location parameter mu. So after successfully describing the location of the curve in a mathematical form, now the next task here is to quantitatively describe the shape of the curve. And we again go by the trial and error method, and we multiply the power of e by sigma and further square it. And let us see as to what is the shape of the graph which we obtain. So here, as it can be seen, as the value of sigma increases, the curve, this bell-shaped curve, it tapers. It comes closer and closer to each. The two ends of this curve, they come closer and closer to each other. But then, as we know, this sigma is a denotation of standard deviation, and standard deviation is the spread of the normal curve, and thus ideally, as the value of sigma, the value of standard deviation increases, the two ends of the curve, they should go away from each other. That is, the curve should start spreading more and more, but this is not occurring here, and thus this attempt to multiply x by sigma fails. So here, after this failed attempt of multiplying the power of e by sigma, now we go with another option, which is to divide x by sigma, and after doing so, we see that as sigma increases, so does the spread of this normal distribution, and this fact fits perfectly with the definition of standard deviation, and thus this sigma turns out to be a desirable shape parameter for the normal distribution. So thus this shape of this normal distribution and the location of this normal distribution can be successfully defined in mathematical terms. But then, as it can be seen in the PDF of the normal distribution, why we have multiplied the power of e by half? Well, the reason here is the point of inflection. The point of inflection is the specific location on a curve where the concavity changes. This means that the curve switches from bending upward to bending downward. Mathematically, it is the point where the double differentiation of the function is 0 and the triple differentiation of the function should be non-zero. But then, what it has got to do with this normal distribution? So, in a standard normal distribution, in a normal distribution which has been designed keeping in mind the convenience with regards the further mathematical operations, the inflection points should occur exactly at x equals to plus 1 and x equals to minus 1. And if we do not multiply the power of e by half, we will find that the inflection points, instead of lying at plus 1 and minus 1, lie on plus under root 1 by 2 and minus under root 1 by 2. And it can also be seen here on these graphs. Here the inflection points, they lie on minus 1 by root 2 sigma and plus 1 by root 2 sigma, and after multiplying the power of e by half, we can see that the inflection points, they lie on minus sigma and plus sigma. Now it is not the case that by not multiplying the power of e by half we are going to defy the concept or we are going to be conceptually wrong, but then it can offer a great deal of convenience and can further reduce the complications with regards the further mathematical operations. And now, very important point, as I had discussed while dealing with the paraphernalia of constants which are present in the PDF of normal distribution, why we have under root 2 pi? Because pi otherwise is something which has got a lot more to do with the geometry of circle and sphere. So then what role does this pi have to play in this normal distribution? So as we know, these two ends of this normal curve, they are like literally from minus infinity to infinity. And those people who have solved problems related to the normal distribution must be knowing that as per the convenience, the area which lies under this normal curve is essentially unity. But then if you take this expression of e to the power minus 1 by 2 x minus mu upon sigma whole square and integrate it with the limits of integration being from minus infinity to plus infinity, as it can be seen on this graph, the solution of this integral turns out to be sigma under root 2 pi, provided you know how to integrate. And if you solve this integration, you will find that the answer is sigma under root 2 pi. But then, in order to make sure that the area under this curve is unity, we divide this equation by sigma under root 2 pi, and thus we can see that there is 1 by sigma under root 2 pi as a coefficient to this power of e. And also here it can be seen on this graph that before dividing this entire expression by sigma under root 2 pi, this graph is denoted by the dotted lines, and after dividing by sigma under root 2 pi, we have this graph in solid lines, and we can see that a considerable part of this graph is spliced down. And now, as the very title of this presentation suggests, we are now coming closer and closer to the multivariate normal distribution. And in order to go closer to the multivariate normal distribution, the very mandatory step will be shifting from 2 dimensions to 3 dimensions. That is, the template of operability is now going to shift from 2 dimensions to that of 3 dimensions. And then what will be the corresponding changes which occur? So the obstacles or the pegs, if we go via the same route of Galton's board, so the obstacles or the pegs in the case of 3 dimensions will transform from being a triangle on the Galton's board to being a pyramid on this 3D platform. And the balls in the Galton's board, after colliding with the obstacles, the balls they used to go only in two directions, either to the left or to the right. But here in this 3D platform, after a bead will collide with the obstacle, it will have infinite number of directions to go to on this three-dimensional plane. But however, the balls or the beads, they will remain as it is, because the entity which they symbolize in the real life, that is the multiple trials, in any case do not change. And it is just this perspective to evaluate this distribution which changes. And even I would like to show as to how the same activity, the same clip of Galton board which I had demonstrated in the second slide would look like in the 3 dimensions. So here, as it can be seen, we have these beads which they collide with this 3-dimensional arrangement of obstacles. They come down and they start forming a heap of beads. It is like a mountain, a small mountain, or like a small hill. So now on the same building blocks, we have to see as to what is going to be the PDF of the multivariate normal distribution. So here we have a top view of the same mountain which we had seen in the previous slide, and this innermost circle, this innermost lightest part, is the peak of the of that curve, of that hill. And here we can see in this PDF, this d, this 2 pi to the power d by 2 corresponds to the under root 2 pi in the univariate normal distribution, and d here refers to the number of dimensions. And as we had seen in the univariate normal distribution, we had only one parameter to describe the location of the curve, but in case of multivariate normal distribution, we would be requiring two parameters to describe the location of the curve. And we can see as to how the location of this hill, this 3D curve, changes as per the change in the value of these two parameters of location, namely mu1 and mu2. So here we can see that as the value of mu1 and mu2 changes, so does the location of this hill, this 3D curve. And as we had seen that the shape parameter sigma, it corresponds to the shape of the curve. So here we have 4 parameters to describe the shape of the curve. Since this is a multivariate normal distribution, so we would be having sigma 1 1, which is the absolute variance of parameter 1 or variable 1 for that matter. We have sigma 1 2 and sigma 2 1, which are the covariances which represent the change in the shape from the perspective of one parameter according to the change in the shape as per the perspective of the other parameter. We have this sigma 2, which refers to the variance or the spread as per the second parameter. And as the values of these 4 parameters change, so does the shape of this 3D curve. Here it can be seen that as the values of these 4 parameters, these 4 shape parameters change, so does the shape of this curve. So finally, after dealing with such a vast background and after dealing with such a long preface, we come to the very essential and the very specific topic, the distribution of the MLE of the parameters of multivariate normal distribution. Now the multivariate normal distribution, as I have said, consists of 2 parameters, namely mu and sigma. And we have to see as to what is going to be the distribution of the maximum likelihood estimate of these parameters. And firstly, we begin with as to what is going to be the distribution of the MLE of mu, which is the shape parameter. And we are not just going to engage in the mathematical manipulations, but we will also see as to how the piece of information which we have written mathematically gets validated visually by the animations. So here firstly we have the distribution of MLE of mu for a p-variate multivariate normal distribution, and it has n independently and identically distributed samples, and we have this MLE given as mu cap, which is nothing but a mean of all the values of xi, and the distribution of this mu cap, which is the MLE of mu, follows normal distribution. But then how can this be visualized? So here we have an animation to validate the same. Here it can be seen that mu refers to the vertical axis of this multivariate normal distribution, and if we give a slice along this along this vertical axis, it gives birth to another Gaussian distribution. That is, it is like a horizontal stack of many normal distributions, many normal curves, which give birth to this multivariate normal curve. And then we come to the distribution of MLE of the remaining parameter, that is sigma. And sigma, as we have seen, is the shape parameter. It describes the shape of this 3D curve, and as it can be seen in this animation, this sigma is like a stack of varying circles, the circles of varying radii, which are kept over each other. These are concentric circles having varying radii which are kept over each other, and they certainly do not resemble the shape of a Gaussian curve, and thus they follow Wishart distribution with n minus 1 degrees of freedom, and this opens up an avenue to another distribution, that is the Wishart distribution. So here I am done with all which I was supposed to say on this topic. So it's the time for acknowledgements. So here is the list of all the resources which I have used to design this seminar and to gather the content for this seminar and to include these animations. So it is a very vast body of resources which I have gone through, and it is the absolute crux, the absolute sum and substance of all these resources which I have tried to present in front of you. So I would like to thank you for your precious attention, for your precious time and your patient listening. Thank you. Thank you very much.